Alright, so to recap our first video, we were dealing with strategies that involved sine and cosine, some combination where sine and cosine could be raised to either odd or even powers, or a combination of both. So here's a couple of the strategies for you. If the power of cosine is odd, you want to factor out a single cosine, and then you're going to let u be sine. If the power of sine is odd, you're going to factor out a single sine and then let u be cosine, because then you'll be able to get rid of either one of those in these cases. If the powers are both odd, then either method can be used. It doesn't really make any difference which one you do. If the powers of sine and cosine are even, then this is when you have to use the half angle identities, which we have right here, and that's what we did in some of those previous problems. All right, so now what we're going to deal with is similar strategies using tangent and secant combinations. So obviously what we need to know is we need to know that the derivative of tangent is secant squared x, and the derivative of secant x is secant x tangent x. So we can factor out as necessary and use the identity that secant squared x equals 1 plus tangent squared x, which is actually developed from the sine squared plus cosine squared equals 1. They all come from the same thing. All right, so let's take a look at our example here. We have the integral of tangent to the 6th x secant to the 4th x dx. So the question is, what do we want to actually try and factor out? Well, in this case, I think the easiest method, let's go green. I think the easiest method here is going to be to rewrite this integral as tangent to the 6th x secant squared x secant squared x dx. And the reason for that is because here we have the identity that secant squared is 1 plus tangent squared. So I can replace one of these with 1 plus tangent squared. By doing so, all of this is going to be in terms of tangent, which means that when I let u be tangent, its derivative will be this secant squared x, which we'll be able to get rid of. So that's kind of the thinking there. So let's go ahead and do the substitution that I originally said using the identity here. We're going to replace secant squared x with 1 plus tangent squared x. So we still have a tangent to the 6th. Secant squared x becomes 1 plus tangent squared x. And then I still got that secant squared x dx. So then our u substitution would seem it would make the most sense to be tangent x. Once again, du is secant squared x dx. Solving for dx, we get du over secant squared x. So let's go ahead and rewrite our integral, making our correct substitution. So tangent to the 6th, stays the same. 1 plus tangent squared for right now stays the same. Secant squared x stays the same. I apologize. We're making a substitution. Let's get rid of those. There, let's try again. Tangent to the 6th now becomes u to the 6th. Then this becomes 1 plus u squared. Secant squared x stays secant squared x, but the new dx over here is du over secant squared x. Again, at this point, the secant squareds are going to divide away, and what we are left with is the integral of u to the 6th 1 plus u squared du. So now we'll go ahead and distribute our u squared. I'm sorry, making all kinds of little mistakes here, aren't I? We're going to distribute u to the sixth, and we should get u to the sixth plus u to the eighth du. Now we can go ahead and take antiderivatives and then do our substitutions. So antiderivative should be 1/7 u to the seventh plus 1/9 u to the ninth plus c. Go ahead and replace u with tangent of x. So we should get 1/7 tangent to the seventh x plus 1/9 tangent to the ninth x plus c. Having a real hard time drawing straight lines. Plus c. That's better. Almost. You get the idea. Alright, so that was if they both had even powers. Now we've got them where we've got odd powers of tangent and secant. So, given that fact, because we can do something with even powers, we want to take one of these things away. And in this case, we probably want to take one of each away to separate out. So I am thinking that we're going to start off with the idea that this is going to become tangent to the fourth x, secant to the sixth x, and then we'll separate off that tangent and secant, which should lead you to believe that we're going to use secant x as our u substitution. That way we can get rid of this tangent secant here. And if we're going to use secant x as our u substitution, we want to put everything here in terms of secant. So tangent to the fourth can be rewritten as tangent squared squared. But we know from up here that if we take this identity right here, secant squared equals 1 plus tangent squared, and solve that for tangent squared, we get the tangent squared is the same thing as secant squared plus 1. So we're going to rewrite tangent to the fourth as tangent squared squared, but remember tangent squared is secant squared x minus 1, and then we'll square that to get our tangent to the fourth. Then we've got secant squared x, tangent x, secant x dx. So now we'll do our u substitution. U is going to be secant x, which means du will be secant x, tangent x dx, and then therefore dx will be du over secant x tangent x. Alright, and I realize again some of you do not write this step, and that's fine if you don't, as long as you can do the algebraic portion of this correctly, you're fine. Alright, so let's go ahead and replace our secants with u's, so that's going to become u squared minus 1 squared u squared. Okay, for right now, tangent x secant x stays there, but when we multiply it by our new dx, which is du over secant x tangent x, we now see that these divide away, and that's going to leave. Alright, I'm going to go ahead and combine this step here. This is obviously gone. I'm going to go ahead and FOIL this. We need to do that in order to take antiderivative. So we're going to get u to the fourth minus 2u squared plus 1. All that times u squared du. Alright, close enough. Alright, distributing the u squared, we get u to the sixth minus 2u to the fourth plus u squared du. And finishing this thing off, we'll take the antiderivatives. 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u cubed plus c. And then don't forget to substitute the original u back. I am going to extend my page just a little bit. There we go. And the original u was secant, so it's 1/7 secant to the 7th of x minus 2/5 secant to the 5th x plus 1/3 secant cubed x plus c. And there we have it. Slightly better box there. Good stuff. All right. It would appear that I have made another mistake. And I did. Let's see. Okay. All the way back up here. Man. All right. Let's use the eraser. Let's do it the right way. That should have been, so all these secants here are wrong. All right, let's go back and fix all this stuff. That should have been secant to the 6th. How I got squared, I'm not sure. That's the 6th. So this one right here is going to be the 6th. Relatively easy mistake to fix, though, fortunately. So now when I distribute the u to the 6th through here, it is going to change all of these exponents from here down. So that'll become u to the 10th, u to the 8th, u to the 6th, which of course is going to change all of our antiderivatives. So this will be different. That'll be different. And this will be different, which of course is going to change these. We'll fill all this stuff back in here in a second with the correct coefficients and powers of secant. Really the only thing I got right was the plus c. All right, let's go ahead and fix this. So the antiderivative u to the 10th, 1/11 u to the 11th. That's going to make that a 2/9 u to the 9th and a 1/7 u to the 7th. So let's go ahead and fix that. Secant to the 11th, 2/9, 9th power, 1/7, 7th power. That looks correct. Silly mistakes, silly mistakes. All right, there we go. All right, so the strategies. If we have combinations of secants and tangents, if the power of secant is even, factor out a secant squared and let u be tangent. If the power of tangent is odd, factor out a secant tangent and let u be secant. Notice it didn't say any combination of the secant being odd. Secant could be odd here, it could be even here. It doesn't really make any difference because you're going to let u be secant. You're going to factor out, if tangent is odd, you need a tangent to be an even power. So you need to factor one of those out, and then we're going to let u be secant so we can get rid of the secant tangent. If none of those methods work, we might need some additional identities. Integration by parts is sometimes used, and sometimes we'll just use a little bit of ingenuity. So if you did not memorize these as a part of ABBC, here's some integrals that you might just want to have in the back of your head. That the integral of tangent, which is not one that we typically deal with very often, is the ln of the absolute value of secant of x plus c. And the integral of secant x is the ln of the absolute value of secant x plus tangent x plus c. If you hadn't memorized those, there they are. They're here for you to use. So we've got the integral of tangent cubed. Again, notice we did not have any strategies up here specifically dealing with just tangents. It does say that if we have an odd power of tangent, we're going to factor one out and do a secant tangent, but we don't have an extra secant in here. So what are we going to do here? Since they're only factors of tangent, we want to rewrite the integrand first. We are still going to split a tangent out. So we get tangent squared tangent x dx. And we're going to change that tangent squared to be secant squared minus 1. So now I have at least in some part created a combination of tangents and secants. What I'm going to do is I'm going to go ahead and distribute the tangent back in now. So I've got tangent x secant squared x minus tangent x. All right, so using properties of integrals, I can split these two things because they're being subtracted into two separate integrals. So now I'm going to have the integral of tangent x secant squared x dx minus the integral of tangent of x dx. And hopefully now you can see, okay, this is something that we just talked about right up here, the integral of tangent of x. We know this one now is the natural log of secant absolute value of secant x plus c. This one on the left now has a combination of tangents and secants. And if we go back up to our criteria, let's see, we have an even power of secant. So if that's the case, we want to factor out a secant squared and let u equal tangent. Well, in this case, I don't really have any factoring to do because all I have is a secant squared. So this is a straight u substitution on the left piece. On the right piece, we already know the result. So on the left piece, u is going to be tangent x. Du is secant squared x dx, and dx is going to be du over secant squared x. So now just dealing with this one, we'll put it in red. I now have the integral of u secant squared x times my new dx, which is du over secant squared x. And then just going to bring this one down. I'm not actually going to go ahead and do the antiderivative just yet, although you can, it doesn't make any difference. Here's my two separate integrals. Let's use black this time to divide out those secant squareds, which leaves us with the integral of u du minus, and I'll go ahead and just put the whole thing in red now, integral of tangent x dx. Okay, this is now an easy antiderivative, 1/2 u squared. This one, now we know, is the natural log, absolute value of secant x plus c, and the only thing we have left to do is go ahead and replace the u with tangent of x. So we end up with 1/2 tangent squared x minus the natural log absolute value of secant x plus c. There we go. All right, so a little bit of ingenuity there by doing some separation of the integrals and then still going back to our standard u substitution here. All right, moving right along. We're actually getting to the end. All right, now we've got one where we just have an odd power of secant cubed. So in this case, you're still going to split it. Let's go back to green. We're still going to split it. Secant x, secant squared x dx. Because the criteria said to go ahead and split that off an even power. The problem is we don't have a tangent x. We could make that a 1 plus tangent squared, but that doesn't do us any good because we're trying to get rid of this piece. So the only other thing to do, and it says hint here, use integration by parts, is we can let u, if you guys remember integration by parts, and if not, here we go, u can be secant x, oops, which means your dv has to be everything left over, which is secant squared x dx. Now, why did I know to pick that? Because I know how to take the antiderivative of secant squared x very easily when I go back to v. So du is secant x tangent x dx, and v, taking the antiderivative, is tangent x. All right, integration by parts. If you guys remember the formula, it's uv minus the integral of v du. uv minus the integral of v du. So uv, secant x tangent x, minus the integral of v, which is tangent x, times du, which is this. So that's going to give us a tangent squared x secant x dx. All right, you might ask yourself, why did I not leave that separated? Well, now because we have this even power of tangent, we can actually put that into terms of secant squared. So let's do that. So this will really be 1 minus secant squared x secant x dx. All right, now we're actually going to distribute the secant x through here. This one's kind of a pain. So now I've got secant x minus secant cubed x dx. This I can split into two separate integrals. Let's slide this page down. We're going to need some room here. So I've got secant x tangent x minus the integral of secant x dx. That minus distributes to that minus, gives us a plus an integral of secant cubed x dx. Here's where the ingenuity is going to take place. First of all, the integral of secant x, we can do that one. That's on the previous page. So far I've got secant x tangent x minus the natural log absolute value of secant x plus tangent x plus this integral of secant cubed. I did something else wrong, didn't I? Shoot. Okay. Easy to fix. Apologize again for the mistakes. This is backwards. Should be secant squared x minus 1. Okay, so that makes that a secant cubed. That makes that one just a secant. And really, the next step is just going to change these. So the secant cubed will become minus. This will become the plus. So this is going to become plus. Yeah, that looks right so far. And then this is a minus secant cubed integral. All right. I knew something wasn't working out right. All right, so what you should notice, and you've probably dealt with this kind of thing before, what you should notice is that this integral of secant cubed x, this is what we started with. This is what we're trying to find. So really, if I put this, see if I can squeeze this in here, the integral of secant cubed x dx equals this, and it equals all the way down, because this is really what it equals. What you should see is that I have a secant cubed x integral of secant cubed x dx equals all this minus an integral of secant cubed x dx. So what if I were to add this to both sides of this equal sign? Well, that's going to give me two of these integral of secant cubed x's on the left. So really what I get is 2 integral secant cubed x dx equals all of this secant x tangent x plus natural log absolute value secant x plus tangent x plus c. And now if I want to solve for this integral of secant cubed x, all I have to do is divide everything over here by 2. So what I get is that the integral of secant cubed x is secant x tangent x plus natural log secant x plus tangent x plus c, all divided by 2. Kind of a long process on that one. How are we doing on time? All right, we're doing okay. We'll finish up this last page, which is very short, and we'll be done with this lecture. Whoops. It's all right, that works out okay. All right, last page here. All right, we can do the same thing, by the way, with cotangents and cosecants using this identity. We're not doing any examples on this, but it's the same general idea as the um, tangents and secants. So you're going to use the same general properties and the same ideas. Finally, we can also use the following identities for sine and cosine if we have things of combinations of multiple angles. So notice in this case, these are not powers. They're multiple angles. So here you have some properties. It says sine of A, cosine of B. So if you have a sine of some multiple angle, cosine of some multiple angle, this is the formula that you would use. It's 1/2 sine of A minus B plus sine of A plus B. And likewise, if you have two sines, likewise, if you have two cosines of different angles. Well, in this case, we have the sine of 4x, cosine of 5x. It fits this first one. Sine of some angle plus the cosine of some other angle. So what we're going to do is we're going to go ahead and rewrite that whole thing, that whole integral, as this combination right here. So this integral becomes the integral of, let's see, this is 1/2 sine of A minus B. Well, A is 4x, B is 5x. So sine of 4x minus 5x is negative x, plus the sine of A plus B, which is 4x plus 5x. So that's 9x dx. All right, we can take the sine out. Actually, I need an extra parentheses in here. That should be around here. That's kind of ugly. You get the idea, though. So let's factor the 1/2 out to the front. Not really factoring it, pulling the constant out to the front of the integral. So what I have is the integral of sine of negative x plus sine of 9x dx. And these are just angles where these are linear functions in here. So again, that trick that we learned in video 1 applies here. So let's take the antiderivative. So we should get 1/2. This is antiderivative of sine is negative cosine of negative x. And then the fact that this negative in here is really a -1. The reciprocal of -1 is just -1. So we just really have another negative out there. Okay, so now the antiderivative of sine of 9x, again, it's a minus cosine of 9x. And then the reciprocal of that is 1/9 plus c. So let's clean that up because that does not look very good. So really what we've got is a negative, negative makes a positive. We're going to distribute the 1/2. So we're going to have 1/2 cosine of -x. Multiply the 1/2 times the 1/9, so we have minus 1/18 cosine of 9x plus c. And that's it. So it really is just using some of these properties that, again, that you probably either haven't really gone into very much or have forgotten since pre-calculus. All right, there we go. That's the end of the trig integrals, and you guys have the homework. Hopefully it shouldn't take you too long or not too difficult, but definitely get the practice. All right.